Good morning all. We are discussing about currents. Consider a line charge lambda moving with velocity v in a magnetic field. Now, when a line charge lambda moving with a velocity v in a magnetic field, what is the magnetic force on that segment of wire? What is the magnetic force on that segment of wire that carries a line charge lambda which moves with the velocity v? We have seen that when a line charge lambda moves with velocity v, it will constitute a current I, that is lambda v. Therefore, the magnetic force on the segment of the wire can be written as integral I cross b dl, where b is the magnetic field through which the line charge is moving. Now, if you observe the diagram, we can see that the direction of the current and the direction of the small element dl are the same. So you can write the equation as integral I into dl cross b, and if the current in the wire is constant, you can take I outside the integral and then it will become I into dl cross b. This is only possible if a constant current is flowing through the wire. Why we can write I cross b dl as I dl cross b? It is because I and dl are along the same direction. So basically F mag, which is equal to integral I cross b dl, and you can write it as I into integral dl cross b. Now this current is called line current. Line current, that is, line current happens when a line charge lambda moves with velocity v along a wire. In another way, we can say that when the charge flows over a line, we can describe it by line current. When the charge flows over a line, we can describe it as line current. Now, what happens when the charge flows over a surface? Now you have surface current density K. Line current is represented by I. In the same way, the surface current density is represented by K. When the charge flows over a surface, we describe it by surface current density K. Now, how do you represent K? K is di by dl perpendicular. So to define the surface current density, you consider a surface on which the surface charge is moving, Now to define the surface current density, you consider a ribbon of infinitesimal width dl perpendicular. Take a small ribbon on the surface with a very small width, an infinitesimal width dl perpendicular, and this ribbon carries a current di. Please note that the ribbon is taken in the direction of flow of current. Here di is the current in the ribbon, and dl perpendicular, it is the width of the ribbon. So to define surface current density, you take a ribbon, carries a current di with width dl perpendicular in the direction of flow of the charge. Then the surface current density K can be defined as di by dl perpendicular. In the same way, you can define volume current density J. When the charge is flowing throughout a three-dimensional region, we will describe it by volume current density J. When the flow of charge is distributed throughout the three-dimensional region, we will describe it by volume current density J. So how to define J? J is nothing but di by dA perpendicular. Now, suppose the charge is flowing through a three-dimensional region. Okay. To define the volume current density J, to define the volume current density J, to define the volume current density J, consider a tube of infinitesimal cross section dA perpendicular. The tube is taken in such a way that it is running parallel to the flow of current. Suppose the tube carries a current di with the cross section dA perpendicular. dA is the current in the tube and dA perpendicular is the cross sectional area. Then the volume current density J is di by dA perpendicular. Now let us go back to the surface current density. That is nothing but di by dl perpendicular. We can say it is the current per unit length perpendicular to the flow. In the same way, the volume current density J can be defined as the current per unit area perpendicular to the flow. Perpendicular to the flow. Now let us conclude. When a line charge lambda moves with velocity, it will constitute a current I is equal to lambda V. In the same way, the surface current density K is sigma V and the volume current density J as rho V, where rho and sigma are the surface charge and volume charge respectively. Now let us calculate the magnetic force in the case of line current, surface current and volume current. The magnetic force on the line current is nothing but integral I cross B dl. We have already seen it. Now, in the same way, the magnetic force on the surface current is integral K cross B dA, and the magnetic force on the volume current is nothing but integral J cross B d tau.